Let's say we have a velocity perpendicular to a magnetic field. Describe the motion of the object of the charged object if it's moving perpendicular to a magnetic field. Gary. We have the velocity of a charged particle moving perpendicular to a magnetic field. Andrew, help me out. It's circular motion, correct. Okay, so it's going to move in a circle, which means we're going to need to draw a free body diagram and do what, Jenkins?
Sum the forces in the indirection.
Because it's moving in a circle, we're going to sum the forces in the indirection, which is going to be magnetic force, which equals mass times the centripetal acceleration. In general, we're going to end up using the fact that the angular velocity is equal to, what's the equation for angular velocity, Tyler? Sorry, say again?
Radius times tangential velocity.
Radius times tangential velocity is not the equation for angular velocity. The equation for tangential velocity is r times omega, but that's not what I'm looking for. I'm looking for just the general equation for angular velocity, the definition of. Sierra? That means change in theta over change in time, which is going to be 2 pi over the period, or 2 pi times the frequency, depending on what you have or what you're trying to find. In general, you end up substituting that in for the centripetal acceleration, which is r times omega squared. Don't forget the concept of the mass spectrometer. The mass spectrometer was composed, there's a picture in the book, we went through it, of the concept of the velocity selector. The velocity selector had electric and magnetic fields which are perpendicular to one another. And from there you can draw a free body diagram, the electric forces in one direction, the magnetic forces in the other direction. And then in the detector, there was just a magnetic field. And therefore, in the velocity selector, you have charges at a certain velocity will move at a constant velocity, hence move in a straight line and enter the detection chamber. And then, because there's just a magnetic field, they will curl in a circle, and you can use the radius of that circle to figure out various information about them. Please say that. Hillary? All right. Biot-Savart. Either Biot-Savant, I have no idea. Biot-Savart. The Biot-Savart Law, which is dB equals mu naught times current times ds cross unit vector r, mu naught over 4 pi. This whole thing is over r squared. This is the Biot-Savart Law. Again, this is an experimentally determined law. It was not mathematically determined, but they did a bunch of experiments and proved this to be correct. This is the equation for the magnetic field that exists around a current-carrying wire. We used this to figure out the magnetic field at the center of an arc or a full circle, but any loop or portion of a loop, and along the axis of a loop. If you recall, we had a current-carrying loop, and we figured out the magnetic field that exists at any point along the axis of that loop. We also used it to prove Amperes Law, which we'll get to in a little bit. We also, I'll do that in a minute. We also figured out the magnetic field around, we'll skip that for a minute. So we can have two current carrying wires and two parallel current carrying wires. We figured out that the magnetic force is equal to the current of 1 times L times the magnetic field for the second, or current 1 times L times mu naught I2 over 2 pi r, because we figured out the magnetic field, our distance from a current carrying wire is mu naught I over 2 pi r, and therefore that the magnetic field is equal to current 1 times current 2 times the length multiplied by mu naught over 2 pi r. Now, I also mentioned that you can use all your right-hand rules to figure out the direction. Oh, let's go through the right-hand rule for the direction of the magnetic field around a current-carrying wire. Thumb points in the direction of. Fingers curl in the direction of. There you go. Those are the two right-hand rules in electricity and magnetism. If both wires are carrying the current in the same direction, the two wires attract or repel, class. They attract. Therefore, if the current is in the opposite direction, the currents are the two wires repel from one another. Okay. We used Amperes Law. So let's get Amperes Law up here. What is Amperes Law, Tyler?
I don't know. It's is there a U-naught in it?
There is.
Okay.
I'll start with that.
Alright. That's all I got.
Travis, how long does he have?
8 sevenths and 4.
No. Oh no, I'm sorry. 8 seconds. I apologize. I'm sorry. I thought you were going to say 8:14, so I got ahead of myself. I apologize. 8 sevenths and 4. Absolutely. Thank you. Sierra, help out. It's a closed loop integral.
B dot ds equals mu naught.
Okay, so we have the closed loop integral of b dot ds equals mu naught times
Current inside
inside the Amperian loop. So we have Amperes Law. In order to use Amperes Law, we need to draw our Amperian loop. And you can see we're going to use this equation. We used Amperes Law to figure out the magnetic field that exists around a current-carrying wire, which we just talked about, which is equal to mu naught I over 2 pi r. We also used Amperes Law to figure out the magnetic field that exists inside a solenoid. For some reason, when you figure out the magnetic field that exists inside a solenoid, a lot of you are forgetting to draw the picture, draw the Amperian loop. What's the shape of the Amperian loop when you figure out the magnetic field inside a solenoid in class? It's a rectangle. You have to talk about all 4 sides and why the magnetic field created by 3 of those sides actually equals 0, and why each one of those is. So the magnetic field in a solenoid is equal to mu naught times, which one are we going to do? N times I over L, which is not the one on your equation sheet. How does the one on your equation sheet differ, please? Matt?
It is the derivative.
It's not the derivative of this. Travis?
Big N over L is just small n.
Okay, and small n is what? The turn density. So capital N would be the number of turns divided by L. Capital N divided by L is the turn density. So it's just a subtle distinction. So we use this to figure out the magnetic field around a wire in a solenoid. And we also did the magnetic field, we figured out inside the wire as well. Don't forget that we also figured out the magnetic field inside the wire. We have Gauss's law in a magnetic field is that the closed loop integral b dot dA is equal to Mohit. Gauss's law in a magnetic field.
dA cosine theta?
True, but I need more.
Well, I mean magnetic flux.
Right, I agree with that.
I don't know.
That's okay. Those are all right. There's something specific I'm looking for here, Winter. It's equal to 0. Why is the magnetic flux, the closed loop magnetic flux, always equal to 0 for magnetic fields? John?
Because magnetic fields are always in loops. It's
Magnetic field lines are always loops. Why is there a quote around the always?
because you haven't found a single pole
A monopole, yeah, because as far as we know, a magnetic monopole does not exist. We have never found one. So if we ever find one, this will no longer be true. Oh, let's see. Faraday's law of induction. Faraday's law of induction, please, Nick. Magnetic flux. And be aware that n is not on your equation sheet, and people are missing that. You remember that n is the number of loops or number of turns, and you need to make sure you remember the number of loops or number of turns. Therefore, this is equal to negative n derivative with respect to time of BA cosine theta. What is the name of the negative? Michael? Lenz's law. Lenz's law. Lenz's. Michael. How do you spell Lenz?
L-E-N-Z.
Nice.
Whoa. 2 in a row.
Where does the apostrophe
Setting
go?
records.
How do you spell Lenz's? Lenz's law.
L-E-N-Z.
Oh, there's no apostrophe.
Oh.
All right, so we have Lenz's law, the concept of electromagnetic inertia. Remember, what people miss on that is, remember, it's the change in the magnetic flux as a function of time. The circuit resists the change in the magnetic flux. The motional EMF. Equation for motional EMF. Sarah Jane Jones.
VBL.
VBL is equal to?
EMF.
I'm going to put delta V is usually the way it is, but yes, EMF would be fine. Again, we have the velocity and the electric potential difference. I'm going to put, just for fun, the sine of theta, because this is the angle between the velocity and the magnetic field, which is often assumed to be 90 degrees. Remember, this is for a conductor moving through a magnetic field. Let's see. Okay, the EMF for a generator. What is the equation for the EMF of a generator, please? Mr. P.
L-E-N-Z.
Close. Closer, but not quite.
Oh, omega t. Or no. Yeah, omega t instead of theta.
Usually sine as well. Well, but I guess my point is, I said usually because it doesn't really matter so much. It just depends on the initial condition, right? So that's not as important. So that is the EMF of a generator. Again, this is something that you should be able to derive, but I also pointed out it is important to also have memorized. Self-inductance. The equation for self-inductance, please. Flash.
Negative L d-I-d-t.
Negative L d-I-d-t. Resistance is a resistance to what, class? Current. Inductance is a resistance to change in current. Okay. Inductance is a resistance to a change in a current. This is, of course, equal to negative n derivative of the magnetic flux as a function of time. Therefore, we got to the fact that the self-inductance is equal to n, the number of turns times the magnetic flux divided by the current. Ooh, I didn't put that up here. How dare I? Time constant for an RC circuit. Andrew.
Is R times C.
R times C. What is the time constant, Jenkins?
It's when the circuit is 62% like charged. 62 point something.
Aha, it's a number. It's an important number, one that I pointed out that for some reason it's helpful to have memorized. What is that number, class?
63.2.
63.2%. Let me point out how you can, if you forget, you can get it from here. Remember, the time constant equals R times C, right? So it's 1 minus e to the negative t, I'm sorry, the negative, where the time is equal to the time constant. So it would be 1 e to the negative RC divided by RC, so e to the power of negative 1. So what's 1 minus e to the negative 1? Plug it in your calculator. You shouldn't know that offhand. I mean,
I was gonna say, like, all right.
0.632. Okay. So if you forget, that is a very simple way to remember. Or not remember. Okay, so then it brings us to an RL circuit. What is the time constant for an RL circuit? De Silva. Class, which one is it? L over R. De Silva, you can't get it. For some reason. Now, well, every time you just get it one or the other way, you can't remember. Okay, so it's L over R. Now, this is, just like the RC circuit, we have a similar equation. I'm not going to walk my way through it. Let's say in an RL circuit, what is, at time t is approximately equal to 0, what is the current when we are putting energy into an RL circuit? What is the initial current? Sierra? It is equal to 0 because remember, the inductance is a resistance to a change in the current. So the initial current is going to be equal to 0 and it's not going to change instantly. So let's come back. We have energy stored where, class, in a capacitor? The electric field. Where is the energy stored in an inductor? In the magnetic field. Important piece to remember. Again, the limits here. So I'm not going to write them down because they're very similar to the equations we have for an RC circuit, but you should be aware of the equations for an RC circuit and the limits of all of those things for an RL circuit. We have the energy stored in an inductor is equal to, energy stored in an inductor, please. Catherine, yeah. 1/2 Li squared. So it is the energy stored in the magnetic field of an inductor. In an LC circuit, you have to be able to identify that it is simple harmonic motion. You have to be able to derive the equation. The second derivative of charge as a function of time is equal to -1 over LC times Q. Therefore, omega, class, is equal to? We'll try that again. Class omega is equal to? 1 over the square root of L times C. Again, we use the fact that omega equals change in theta over change in time, or 2 pi divided by the period to figure out the period, or the frequency. You then have the equations for charge as a function of time, for example, which is going to be equal to Q max times the cosine of omega t plus phi.
That was pretty good.
Ladies and gentlemen, people, have a beautiful day.